Come here. Perhaps the other one.
This mic is
very loud.
yeah. Let's stand over here. And I don't need help to be louder. Welcome everyone to Netvc.
More behind the speakers, maybe?
No, don't give me instructions that are going to make it awful.
Okay.
No. Oh gosh.
Take that mic.
Yeah, that's. Hello, hello, hello. That works, right? Okay, good. Haha. So welcome everyone to Internet Video Codec or Video Codec Netvc. This is our only session this week. So we have a relatively packed agenda, but let's go through our introduction slides. We need a Jabber scribe, almost a Jabber subscribe. Our Jabber room is netvc@jabber.ietf.org. Do we have a Jabber scribe? It's an easy job. Oh, thank you very much. So, thank you, Jonathan, for nominating yourself to be a Jabber scribe. We also need a note taker. We just need light notes, and so decisions, various things people are discussing. Come on. I'll play the Jeopardy music in a minute. Don't make me sing.
1 or 2 votes off each person.
Yay! Thank you so much. Sorry, what's your name? Tessa, thank you very much. Sorry, thank you, Tessa. So Tessa will be taking notes. However you wish, Tessa, it's up to you. Blue sheets are going round. As per normal, we will have. Actually, do we have some? We do have one remote presentation today, right? Okay, so please say your name clearly and loudly at the mic so that Tessa can get it down on the notes properly and that the remote presenters will know who is speaking. I will try and speak slower as well. Okay, next slide. Thank you. Note well. People should be quite familiar with the note well. If you're not, it's there. It's also on the site in probably much larger font and legible and updated. So please look at the note well on the IETF site. I mean, generally, it's the same type of thing. Okay, please take a look at the note well on the IETF site. It's very important for you to understand. Please do not pay attention to what's on the screen in front of you. Okay, next slide. I think, oh, right, so an agenda. Have we updated this recently? Is this relatively updated?
This is the current agenda. So the only thing is that
Cool.
During the chair slides, Alexei will jump in to present the requirements document status.
Great. Okay. So let's people take a look at the agenda. Any agenda bashing? Woohoo! We're set to go.
And the one thing is, Tim, you're going to do both. You're going to do Thomas's testing document and the DALA 81 update, right? Okay. So one sub.
Okay, we're ready to jump straight in then. Okay, so
One thing is I don't see Alexa.
let's try that, but you might just want to take a step back.
Okay, so I'll improv, and well, technically he's not. He may have thought it starts at 4 o'clock. Anyway, it's a brief update. So the requirements document. Wow, that's really good. I'll just back up.
Keep on using that.
Yeah. How's everyone enjoying this on the remote side? Periodic booms of. Okay, now that everybody's muted their headphones, the requirements document is basically ready for progressing. So we're at version 6 right now, and there was a few changes in that version. It was mostly around section 311, calling out that that the objectives for compression efficiency are really applied to all of the use cases that are defined earlier in section 2. So before, it was trying to call out some specific use cases like natural content as well as screen sharing content, and rather than enumerating things, it's just better to go ahead and reference section 2, which has all of the use cases. So the compression efficiency targets apply to all of those use cases. And there were no other substantive changes. So where we are with the document right now is we completed the workgroup last call after this update, the 06 update. That was back at the end of May. And the current status is that we'll be doing the Shepherd write-up and passing this on to our AD. Which is where? Adam is in the room or not? Okay. You must have been standing outside listening. Okay, so we do have an AD. Yeah.
Was there a question? Or was it just
No.
Okay.
Just a heads up that the requirements will be progressing to the Shepherd write-up will be progressing to you hopefully this week. All right. Any other comments on the requirements? And one of the questions earlier was about whether or not we publish this, and the main impetus for publishing it was that it's also being used in other bodies as a set of requirements for new codec design. So there's value in publishing it even beyond IETF members. Okay, that's it for requirements. So let's. Tim, you want to come up for testing?
Excellent. Can people hear me? That doesn't really sound like it's on. All right. All right, that better? Yes, I can hear that now. All right. So I've looked at these slides for about 30 seconds and didn't make them, so this should be great. So there hasn't been a lot of changes to the testing document. What we have done is gone through and started exercising some of the subjective test portions of it. So there's a subjective testing procedure defined. Basically, we're using the same codec and command line configuration as all of the objective tests, but we only select one quantizer for both high and low latency to test visually. We added a subjective test set, which is basically just a small subset of the full objective test set, because we have to actually manually look at these, so smaller is better. And we have implemented a tool in Are We Compressed Yet and the analyzer, which supports subjective testing. So basically, it gives you a split view or lets you flip back and forth between the videos, and then it randomizes the presentation order, and you vote for which one you think looks best, or if there's a tie. And there's instructions that it shows the voters for all that. All right, next slide. So the statistical analysis side, generally you need about 12 viewers to get results that are significant. That doesn't mean it's not a guarantee that if you have 12 you'll have significant results, but you need probably at least that many. So all the voting is prefer A or prefer B, so there's no indication of how strong that preference is. And then we test for significance using a sign test. For all the people who vote tie, it basically counts as half a vote for and half a vote against, or half a vote for A or half a vote for B, however you want to think about it. But the main effect is as you get lots of ties, it becomes much harder to have a significant result. And then all p-values under 0.05 are considered significant. All right. So subjective 1 is a test set, is a subset of objective 2 slow. and these are the 5 videos in there. One thing we should point out is that using a QP of 50 for Cintel actually looked quite bad. So we're probably going to revise that to use a lower quantizer, because even with 50, which is the highest quantizer we have of any of the videos, it still looks like a blocky mess. So that's something that will probably change in the future. Next slide. And so we have a few examples of some of the tests that we've done. So one of them was a test against the constrained directional enhancement filter versus the old constrained low pass filter that was in Thor. So Steiner was going to talk a little bit more detail about those during his presentation. But those are a couple of links you can go click on or even type in this. They're short enough. So you sort of get an example of the kind of tests that we've running. So these have all completed at this point. So while you're welcome to go ahead and vote on things, we've already tallied the results there. If you're curious, CDEF wound up being significantly better than COPF in at least for several of the videos that we tested at a statistically significant level. It was better than CLPF for all of them at a not statistically significant video level. We also did some deblocking filter tests, trying to determine whether we really need to keep a 15-tap deblocking filter or a 7-tap deblocking filter, and you can see some of those examples there. Is really Cintel video only twice, and I don't actually remember what the difference between those two were. I think they were just different versions of the code base, but I could be mistaken.
Just remember to use the mics, because there are people actually in the Meet Echo now.
Right. The question was, is it really? Do we really intend to have Cintel video only up there twice? All right. Next slide.
I think that's it. So if you want to, I'll jump to an example of this if people are interested. I think I have one loaded. So that's what the subjective test looks like, the interface. There's a little tutorial to guide you through it. And if Netvc is willing to be guinea pigs for doing the subjective testing, we'll be happy to start forwarding all of the subjective testing requests to the list, and people can start evaluating the tools that we're looking at. Yeah, this the resolution on here is killing it. This is, I think, designed for 4K. I think we're getting VGA to this projector.
Yeah. So at Mozilla, we actually have a 4K monitor set up in the kitchen. We make the interns do a test before we give them cookies.
Yeah. Yeah. So.
You don't have to request a 4K projector if you want, right?
Well, I'm sure this projector is not the problem. It's how we're connecting here is it's going through VGA, so it's getting some crap VGA resolution instead of. I'm sure it's a 1080p projector.
There is an IETF owned 4K projector they drag around. That's owned by the venue.
Mm-hmm.
Right. You can ask for the special IETF owned 4K projector.
Okay, we'll make sure to ask for that next time. Yeah, didn't know it existed.
Pretty much.
Yeah. Okay. So that's the example of the interface, and you can do the, like Tim said, the voting is closed for these current things, but for new subjective tests, we'll start forwarding them to the list if people are willing to give their feedback on them. All right. Thanks, Tim. Okay, so next up we have Steiner for the Thor AV1 codec update. Your slides were really big because you had a lot of graphic. It was only a few megabytes. I'm surprised it's this slow. probably too late to switch now. Whatever I'm on, I'm on.
Well, I will give you an update on Thor, and I also have an update on the compression complexity trade-offs that we have for the royalty-free codecs. Yeah, this takes some time, it seems. I probably didn't compress the graphics that well. I hope this is not just the first slide.
No, it's got previews of all of them, so it's it knows that there's 13 slides coming down.
See the bar walking across.
Yeah, we're at 75.
Yes. It's looking very much like the way it's meant to be back.
And I see it did select the IETF hotel, so
Yeah.
I am on IETF hotel,
Which is good for the
which is ironic that it associates to that AP then.
Apple's notion of ordering Wi-Fi networks, it prefers the ordering over the strength. There's no way to say, you see multiples, pick a strong one.
It will pass.
Go what?
Pass.
Okay. Well, supposedly we're done. You know what? I have a local copy. Just, you didn't update anything, right? Oh, there we
Okay.
go. The threat of a local copy got it going. Okay.
Great. Yeah, just jump to the next slide, please. So there's no updates in the GitHub repository since Chicago, but there's still some work that has been done. I think the consensus in Chicago was that we should aim to have both Thor and Dala converge. And so that would include merging the loop filters, the Dala D-ring and CLPF. And John Mark presented how we did that for AV1. And so I began doing that for Thor as well, but I haven't quite finished yet. And also, Thor is lacking proper entropy coding, so that's also on the list. So some work has been started on that, but that's going to require more work than finishing CDEF. And also on at least my wish list was a new tool for improving screen content in Thor. That would really help, but that work hasn't started yet. And also, since last time, we have changed the CDEF design slightly, and I'll get back to that in, I think, the next slide. So the original CDEF design had a directional filter, which corresponds to the first Dala D-ring filter, and then a cross filter corresponding to Thor CLPF. And the second filter is applied on top of the first filter. That gave some hardware concerns over line buffer requirements, because both filters can have vertical filtering. So when you apply it on top of each other, then the line buffer requirement increases. So that was originally addressed by restricting the second stage filter in certain cases. But I think that was really a quick fix. So I tried to find a better way to do that. And I think what I tried is both a simplification as well as solving this issue. So what I did was to combine the two passes into one. And by doing that, I get a new filter with a lot more tabs. And the tabs are divided in two groups. We have the primary tabs, which correspond to the original directional first pass filter, and secondary pass, which correspond to CLPF, except that it's now made directional, just like the primary filter. And the clue is that you can specify different strengths for each of these groups of tabs. And that gave no significant change in BDR, actually as very tiny improvements, and we got actually a gain in chroma. Next slide, please. So these are the tabs. The first 8 matrices are the tabs for are the primary tabs, which will have which will be weighted with the primary strength, and the lower matrices are the arrangement of the secondary tabs, which will have a separate strength. And in the single pass filter, I tried both this set of tabs and also a few more tabs, extending the upper 8 matrices to 7 by 7 fields. So there were 2 extra tabs, but that didn't change the objective results. So this is what I'm currently implementing for Thor. Next slide. So these are the objective results, comparing the 2 pass with the 1 pass filter. So negative numbers means that 1 pass is better. And in Luma PSNR is about 0.2% better, which is close to the noise range, but at least on the right side of this is 0. And if you look at the chroma numbers, they are better. And in particular, if you look at the CIEDE numbers, which combine Luma and chroma, we get about 0.5%, which I think is it's not much, but it's nice for something that's really a simplification. Next slide. So as Tim mentioned, we now have a test framework for doing subjective tests, and one of the tests compared CLPF to CDEF, and this was the 2-pass CDEF, but I don't think the 1-pass CDEF will be that much difference. The tests were done in AV1, but again, I don't think that will be much different from what we would see in Thor. And as Tim mentioned, there was a significant preference to CDEF in some cases. Those were in the low latency cases. For the high delay, high latency cases, there were no preference. But still, CDEF got more votes than CLPF for every sequence, both in low delay and high delay. The numbers were just not significant. So for some sequences, CDEF wins, and for the rest, there are no clear subjective advantages. But in all cases, I think the objective scores for CDEF are slightly better. Next slide. So these are the results. Red is the vote count for CLPF. Gray are the tie counts, and CDEF are the green bar. And in all cases, there are more votes for CDEF. And in 2 cases, the difference is significant. And this is for low latency. If we move on to high latency on the next slide, there's no significant difference. But again, CDEF has more votes than CLPF. The main difference is that there are more ties, and that's not that surprising, since in the high latency case, the loop filtering has less effects. So I think these results are to be expected. Next slide. So I'd also run some other experiments in RV compressed yet, looking at the objective numbers. I wanted to see how the compression and complexity trade-offs are looking. So I have been using two test sets, the regular objective 1 fast. I didn't use objective 2 fast because from some time to time the objective 2 fast test set breaks AV1. It might have been fixed now, but I made a test so that we could see how AV1 has been doing over time. So then I needed to do it with the old test sets. And also I selected a subset of objective 1 test, which is just video conferencing content. So that would be the 720p subset of objective 1 fast. And I found that AV1 compression has significantly improved since Chicago, both for low and high latency, but also the complexity has increased, and quite a lot. I also ran Vp9 and AV1 in both error resilient and non-resilient modes, because Thor is always error resilient. So in order to do a proper apple-to-apples test, I did both. And where I compare the different codecs, I use Thor in high complexity, low latency mode as the BDR anchor. Next slide. So this shows the compression history of AV1 over the past year. So on the left side, we see how AV1, that's AV1 1 year ago used as the anchor. So over the past 12 months, the compression gains are slightly more than 20%. And if you then move on to the next slide, we will see what happens to the complexity.
So just to clarify, the left is a year ago and the right is today?
Yeah.
Okay, so it dropped from 0, the anchor a year ago, to minus 20% today?
Yeah, slightly more. And most of that has come in the last 3 months. So if we look at the complexity, and here the y-axis is logarithmic, and it also shows frames per minute and not frames per second. So it started a year ago with about 23 frames per minute, and the latest code will run the same sequences at 1.9 frames per second. Sorry, per minute. Yeah. So that basically means that in order to get to a 20% gain, the complexity has gone up by about 1,000%. So the compression definitely comes with a cost. Next slide.
Quick question here. Do you know what the uptick was? I'm surprised that there was any lowering of complexity. Any idea what the uptick was?
Well, I suppose the reason is that somebody enabled a tool just to get the tool in and did the optimizations later.
Okay. Maybe Tim knows better.
Yeah, Tim Terryberry from Mozilla. I'm not sure exactly which commits Steiner measured, but one possibility is there were some changes to select which reference frames to use for each block independently of searching all the possible coding modes for that block, which allowed you to make much quicker selections of which reference frames to use. So that was something that happened after we expanded from 3 reference frames to 6 reference frames. So the expansion probably made it much slower, and then speeding up that selection may have made it faster again.
So over the last 3 or 4 months, there have been a lot of new tools being added to the code base and enabled by default. And I'm sure that that has happened without the optimizations being fully done. And also some of the tools compete for the same gains, and there still is some work to get a proper integration. So the complexity could go down.
And for this work, you took how many data points to sample? You took like monthly data points?
No, every 2 weeks or twice
Okay.
a month, actually.
Okay, and the same configuration all the
Yeah.
time?
Right.
So it's whatever people turned on by default?
Yeah.
Okay.
So the dip there, I could just have been unlucky in picking that exact commit because that was selected. I selected whatever was in the repository on the 1st and 15th of every month, I think. But it does show a trend, and it roughly corresponds to the compression. So basically, higher compression comes with a cost.
Yeah.
Okay, so if we move on to the next one, we'll compare the different codecs. I'm comparing Thor, Vp9, and AV1. I wanted to have X265 in this plot as well, but currently that doesn't work with RB compressed yet. So I didn't manage to get that in time. So the red graphs are AV1, and the purple Vp9, and the black Thor, and the dashed graphs are the non-resilient runs of the codecs. So, and this is comparing Thor with the other contexts, other codecs with mixed content, which is the in this case the objective one-fast test set. And we see here that Thor and Vp9 seem to have about the same complexity and compression trade-off, except that Thor can add some more compression at the cost of added complexity. And AV1 in this plot is performing better. But I think that if we can get the screen content tool into Thor, the situation would change. Next slide, please. So if we limit the sequence test set to just video conferencing content, then Thor is performing much better actually than Vp9. And it's quite close to AV1, not quite, but here we see that AV1 will add better compression, but again at the complexity cost. So this is perhaps this is perhaps what the previous slide would look like if we could add some good tools for screen content and perhaps a few other tools. So basically, I think this tells us that it's possible to get Thor to perform roughly as well as AV1, but with a fraction of the tools and with lower complexity. And I think that was the last slide.
Do you know offhand what amount of screen content is in this earlier test set, this mixed content test set?
I I don't remember how many sequences, but I do remember that there was at least one sequence which, in some cases, had, I think, around had a BDR score of 80% better than Thor.
So there may be outliers really skewing the distribution. Minecraft.
I can't remember which one, but one sequence added several percent to the total.
Yeah. So Tim Terryberry again. You're probably thinking of Wikipedia, which is
Right.
a screen capture of somebody scrolling through a Wikipedia article. There is also a few Twitch videos, one including Minecraft, which may benefit from the screen coding tools, but I don't think it was nearly as large as the benefit for Wikipedia.
Right. And this is Thor without any of the work in progress. So with CDEF, we should get a slight improvement. Not a big one, but at least something. And for a proper entropy coder, I don't really know how much that will add, but it could be a few percent.
You don't anticipate very much complexity cost for either of those two tools? Or
The new ones?
yeah.
So CDEF will add some more complexity over CLPF, but it's not that huge.
Mhm.
We're speaking of a few percent of running time, depending on the complexity setting.
All right.
And for the entropy coder, it will likely add some complexity, but again, it's not a doubling or something like that. And well, the screen content tool, it hasn't been invented yet, so it's hard to tell.
Just to clarify, there are screen content tools in AV1.
Yeah.
Yeah,
So there's one tool giving a huge boost to the Wikipedia sequence and a few others. So that's worth looking into.
Any other questions? All right, thanks, Steiner. So next up, we have Tim for the DAL update. And hopefully you didn't add a bunch of graphs and pictures in yours. Oh, no, much better. There we go.
There are a few, but they're small.
Okay.
All right, so I'm not Thomas Dady, but he did most of the work for this, so his name's on the slide. So basically wanted to go over this change, which is something that we discovered while working with the Vp9 RTP specification and thought, that's not great, maybe we could make that better. So basically had a couple of requirements. Next slide. If you want to actually do something like temporal scalability, it should be possible to determine and control which previously coded frames are dependencies of the current frame, right? So if I have a bunch of layers, like I want to know when can I actually drop a frame, and I want to be able to construct the layers in such a way that I can drop frames and I don't break anything. So for example, allow skipping every other layer to get some kind of, every other frame to get some kind of temporal scalability. Next slide. Conversely, if I want to have error resilience, then it should be possible to determine if the decoder is missing a frame that's required for decoding. That way I can ask for it again, or I can decide to drop some frames, and that lets you build a decoder that never shows a broken frame. So this is sort of like the previous case, but instead of me intentionally deciding which frames to drop, sometimes I just won't get a frame, and then I have to figure out how to handle it. All right, next slide. So let's talk about how this works for Vp9. So there are a bunch of reference frame dependencies. So basically, you're allowed up to 3 reference frames. Each frame can reference up to 3 different frames out of a pool of 8 that the decoder maintains. And these are implicitly or explicitly signaled with picture IDs in the RTP mapping. So the implicit version is basically you just set up a pattern that gets used over the whole group of pictures. And the explicit version, just in the frame header, it has a list of up to 3 picture IDs, and those are the ones you reference. But then there's this other set of dependencies, which come from what Vp9 calls frame contexts. What these basically are probabilities used for the entropy coding. So Vp9 stores probabilities that are backwards adapted based on data from previous frames, and the decoder maintains 4 independent sets of these probabilities, and then each frame signals which one it wants to use, and can optionally write back to that same set the updates based on the data that was decoded from the current frame. So this choice is completely uncorrelated with your reference pictures or picture IDs or any of that other stuff. So next slide. As you can imagine, this creates some problems. So if you lose a frame, in the error resiliency case, you don't know which slot it updated. So you actually no longer know if you could decode any frame. But also, the last frame to update the slot you're using might not have been one of your reference frames. So if you're going through your RTP headers and saying, okay, you know, do I have all the frames I need to be able to decode this for the current layer, or can I safely drop this frame and not break anybody else? You don't actually know unless you parse into the packet and figure out which of these frame context slots it's updating and what other frames that affects. So there are a couple of ways that we could handle this, but basically what's happening here is we've introduced this potential hidden 4th frame dependency. And for people who are designing RTP mappings, this is surprising because everybody thinks, oh, I told you what reference frames you use. That's all you needed to know, right? But actually, there's this extra mapping, and the extra dependency in the RTP mapping only signals 3 picture IDs. So there's a couple of ways we could fix this. We could signal a 4th picture ID. We could impose some requirements in the encoder that, you know, the slot you use must have come from one of your reference frames. That's a discussion that we'll have on the payload list to figure out how to handle that for Vp9. But we thought for an X codec we could do better. And then the final problem is you can't fork probabilities and involve them independently because of the requirement that you can only write back to the slot you read from. So if you basically what that means is that every layer, if it wants to have its own independent set of probabilities, it has to pay the cost of adapting them from the static defaults independently of all the other layers. So you don't get to share any of that overhead. Next slide. So we've made a proposal for AV1, but the problems, AV1 basically has all of these same problems and then more problems on top of that. So one change that AV1 did make is that it now explicitly signals the frame IDs in the codec payload instead of having it in the RTP header. So that's actually good. That means it gets consistently done the same way everywhere. It now allows up to 6 reference frames per frame, still draw from a pool of 8. It handles probabilities basically the same way as Vp9, but now you have 8 slots to pick from instead of 4. And then it's added some new things on top of that. So there are now motion vectors stored from previous frames to use for temporal motion vector prediction. And the original design was that it just always picked them from the last coded frame. And if you were coding things in such a way that the last coded frame wasn't going to be available, or you didn't want to rely on it being available, then you just didn't have temporal motion vector prediction. Sorry, you couldn't use it. So that was sort of fixed up by this TempMV signaling proposal, which I'll talk about in a minute. And then people kept adding more things like global motion data, which is now coded as deltas relative to the last coded frame, which again, if you want to be able to drop the last coded frame, is a problem.
I'm Mosin from the floor, Mike. I just comment on the first one. For resilience, there's also, I'm not sure what you meant by frame IDs there, but for resilience, we also have these frame numbers now that have been added that are beyond just, you know, which one of 8. You can actually have a much larger frame number. So like, you know, a 10-bit, 12-bit frame number. That way, if you drop one, you actually know that you dropped one. You know that.
Yeah, that's what I meant. So basically, it's the same as the picture IDs in the Vp9 RTP mapping.
Right.
I think they're not necessarily the same number of bits, but similar idea.
Okay.
So what we wanted to do is have some consistent way of solving this problem as we accumulate more and more of these hidden dependencies. So next slide. So we came up with a very simple proposal, which is just make all of the dependencies between frames track with the reference frame structure. Next slide. And that's the wrong version of the slides. So there was a nice diagram there that maybe Mo will be able to pull up.
Or it didn't successfully convert to PDF.
So it didn't successfully convert in the first version I sent him, and then I immediately saw that and sent him a second version.
So I can work faster.
You don't want us to see what you want.
No, it's give me a quarter of my screen on that stupid VGA. Okay, so yeah, the 66K one.
Yeah, no,
There's one up.
200 something K.
At 3 a.m. Okay.
Yeah.
You don't sleep?
Jet lag? You didn't know that?
Okay.
What jet lag?
What is this thing?
Okay, so here we go. Is that the before?
Yeah. So this is basically the situation now. You have this pool at the top of reference frames. Each one of them has a buffer of actual pixels in it. And as I said before, we have these temporal motion vectors that get saved for use for motion vector prediction in future frames. And with the temp MV signaling, what they did is they just moved that buffer into the reference frame buffer. So every reference frame has a copy of the motion vectors that were decoded with that reference frame. And then when you pick your list of references to use for the current frame, then the first one becomes the one that you use, that you draw those motion vectors from. But then down at the bottom here, there are these frame context slots that have all the probabilities in them, and those are, you point to some index in that table, that's just coded in the header completely independently of all the reference frames, and then you have this global motion data, which is just always taken from the previous frame. And if you don't want to use the previous frame, then I'm sorry, you don't get to use global motion. All right, and so with our proposal, it looks more like this. So basically, we move all the probabilities up into the reference frames as well. And also the global motion data, though this diagram, yeah. So in practice, we've only implemented part of this proposal, and in fact, we have not moved the global motion data up yet, but we will. So yeah, pretend that it isn't pointing to the previous frame down there at the bottom anymore. So now what happens is whatever is the first frame in your list of reference frames, you now draw not only the reference pixels, but also all of your motion vectors, all of your probabilities, your reference global motion data that you predict from. So everything just comes out of that first slot you're pointing to.
John, thanks. Why did you make it the first slot rather than the selectable slot? You just don't want to pay the bits for the selection cost?
I don't want to pay the bits for the selection cost, and coding fewer things in the header is generally good from an IPR perspective.
Presumably you were previously coding the probabilities, right? So the probability selection. So
yes. So previously we were coding an index for which set of probabilities to use, and now we're not.
So you're actually saving bits.
Yes, we're saving a whole 3 bits per frame. All right, next slide. So basically, we remove all of the frame context slots, and those just are now reference frame slots. We remove all of the syntax elements for saving and restoring frame context, so it's actually more than 3, because I also had to code a bit to say whether I wanted to write back to that buffer. And instead, we always save a frame context with a reference buffer. So whenever we would store a reference frame into one of those slots, we also store the updated probabilities from the current frame, the temporal motion vectors, the global motion data, et cetera, et cetera. We also no longer need a syntax to reset frame contexts. So what happens is on a keyframe, then we just reset all the reference frames, which includes resetting the probabilities and everything else. On an intra-frame, on an intra-only frame, then we reset that one specific reference frame that the intra-frame gets stored back to, but not any of the others. So that's an intra-only frame that is not a keyframe. Next slide. So there are a few complexities with this. So there's now, as Jonathan Lex points out, this interaction between the reference number in that list and what its function is. So in our current encoder, basically the first reference was always the last frame, the most recent frame from the same layer. And so now you need to reorder that reference list to use probabilities from your if you want to use probabilities from your long-term reference or from an alt-ref or some other type of frame, you have to reorder that list, but that's just a mapping in the encoder side. It shouldn't have any functional changes. So as I said, if we have an intra-only frame that is not a key frame, there's currently no way to use a previous frame context. So basically, just your probabilities always get reset. That's the same way things worked in Vp9, and we didn't change that because we didn't think it was that useful. And finally, previously you could have probabilities from a non-reference frame, and now you can't, just because there's no way to code that. But since we now can list up to 6 of our 8 potential references as references for the current frame, the impact of that seems kind of low. It seems like whichever frame you want to draw probabilities from, it's probably going to have some useful pixels in it to predict from, and if not, there's some other frame that you could drop that wouldn't have been that important anyway, with a list of 6 of 8.
Real quick, do you mean to say that you could before you could update a context after decoding a non-reference frame, and now you can't because the contexts for pixels and other data are all mashed together in one?
No, so if you're decoding a non-reference frame, yeah, you could in fact update a context and then use that in some future frame and correct. Now, if nothing ever references it, then you can't use those probabilities. So you have to write them back to be able to use them. All right, next slide. So as I said, there's still some things to move into the frame context. One is this: the global motion thing is relatively recent, and so we're doing that as part of the global motion proposal, which is not complete yet. So that hasn't happened. And while we were working on this, people started doing frame size prediction based on the previous frame as well, and so now we need to move that in there too. But the main proposal is still put everything in this frame context inside of a reference frame, and so the main idea doesn't change. So it can handle all these new things that people are adding. And I think that's everything on this proposal. Did anyone have any questions about how any of that works? All right. Then I will switch gears and talk about a completely separate topic. So I'm also not Luc Trudeau or David Michael Barr, but again, those are the people who actually did all of the work that I'm about to talk about. And the tool I'm going to talk about is Chroma from Luma. So next slide. Basically, we have changed this a lot from previous proposals. The stuff I'm going to talk about now is basically an evolution of the stuff we presented in draft EGI Netvc CFL over a year ago. We've changed essentially everything. And this is complementary to the proposal in draft Mitskogen Netvc ChromaPred, which is a variant of CFL used for inter-prediction. So what I'm going to talk about is solely used for intra-prediction. Right, next slide. So for those of you wondering what chroma from luma is, the idea is to try to exploit local correlation between the different color planes. So if we start with the original over there on the left, if I just reconstruct the luma and then do DC prediction for chroma, I get sort of this flat color, flat constant color there, which is not great. But if instead I build a linear model and try to predict the chroma planes from the luma planes, I actually get something that looks pretty close to the original, even with just a relatively crudely quantized linear model. All right, next slide. So originally we had designed CFL to work within DALA, which is a primarily frequency domain based codec. So in DALA, chroma from luma predicted frequency domain coefficients directly. That's hard to do in other codecs, particular in AV1, for example. There are up to 16 different transform types, and the luma transform type might not match the chroma transform type, and the luma transform size may not match the chroma transform size. And we had a way of that last one could sometimes happen in DALA, but since everything was a DCT, we sort of had a way to do mapping from one to the other. But now if you have to expand that to work with all the different transform type combinations, this gets really complex and hard, and so we gave up and said, maybe we should just do things in the spatial domain after all. However, there was one lesson we did learn from DALA that we are taking advantage of, which is that a lot of these chroma from luma proposals try to build the linear model implicitly based on previously decoded data, and it actually turns out that that's not great. So when it works, it does okay, but when it doesn't work, it can be really, really bad. And so what we said instead is, how about instead we just explicitly signal the model? When we did this in DALA, we actually got a small gain compared to trying to build it implicitly. So that we're going to continue to do. All right, slide. So sort of compare this against things other people have done. LM mode is the HEVC proposal, the original one. Thor CFL is the draft Mitskogen I talked about earlier. DALA CFL is our previous work, and then the proposed thing over there on the right is what we're doing now. So we moved, compared to DALA CFL, we moved back from the frequency domain to the spatial domain. Like DALA CFL, we are now doing explicit signaling of what the linear model is. The actual signaling is a little bit different because we're no longer using PVQ, which if people remember is our perceptual vector quantization. So we've basically just added a new interprediction mode that is only used for chroma planes, so it's UV specific. And so that signals when to use this. And then said we no longer require PVQ because we're doing everything in the spatial domain. And now when we, on the encoder side, we don't do an explicit model fit. We actually just search all of the possibilities that we want to encode. And then on the decoder side, we just use the signaled parameters that were sent, and so we don't have to do any decoder model fitting, which makes our decoder nice and simple, which is always a good additional side benefit. Next slide. And so on the encoder side, things look like this. So we start off with the reconstructed luma pixels up there on the upper left. And then we're going to average them over an entire transform block, which computes a DC value, right? So the idea is our linear model is going to have some constant offset, and we want to factor that out and code it as just a regular DC residual as you would with normal transform coefficients. So we average luma pixels over the whole transform block, and then we also do any subsampling that we need to do to convert from 444 down to 420, and subtract off that constant offset. And so now we're left with basically just the contribution to the AC coefficients, but still in the spatial domain. And we feed that into a search for the best linear parameters, one for each of the two color planes, CV and CR. And then on the bottom there, we take the original chroma pixels, and we also want to factor the DC term out of chroma. but since the decoder doesn't know what the reconstructed chroma looks like, we just do DC chroma prediction as the sort of the best guess is what the DC will be. And we subtract that out and feed that into the search as well. And then the search searches over all of the possible choices of alpha for each color plane and explicitly codes that out to the bit stream. So there are a couple of choices here that we made for efficiency reasons. So when we have a prediction block, we can then subdivide that into multiple smaller transform blocks. So when we do our Luma average, we do it over just a transform block, which lets us do reconstruction transform block by transform block and basically minimizes the amount that needs to be buffered in hardware or things like that. Conversely, when we predict DC for chroma, we actually want to predict it over the entire block at the start. So we could instead have chosen to update that after each transform block is coded, which could potentially give you a more accurate prediction, but then it makes your search really hard because every time you pick a different alpha, you have to do a full transform and reconstruction to figure out what the DC prediction for the next transform block would be, to figure out what the error impact of choosing your alpha would be for that transform block. So doing the DC prediction over the whole prediction block at once avoids that whole problem. All right, next slide. Then the decoder side is again pretty simple. We do the same averaging and subsampling of the Luma pixels, and then we scale them by the signaled alpha values and add that to our chroma DC prediction, and that gives you a CFL prediction that we then use for the chroma planes. All right. And my slide advancer has just stood up.
Question about your from the floor mic. One question about your alphas. Do you ever look at component by component? As say you had an alpha for CB computed, does that ever feed into CR? Or have you ever looked at to see whether or not one plane's adjustment from Luma is useful for the other plane?
So right now they're jointly coded. So basically what happens is we code an angle in a plane of alphas. So you have a two-dimensional plane of alphas for CB and alphas for CR, and we code a direction in that plane and then a magnitude along that direction. So to the extent that they predict each other, what will happen is probabilities for those code points will increase, right, to the extent that those two are correlated.
Okay, so code diagonal instead.
Yeah, exactly. And of course, there are complications. So the first one is for sub 8x8 block sizes for 420 and also other chroma subsampling formats. So what happens for 420, if your Luma blocks are smaller than 8x8, we don't want to have transforms that are smaller than 8x8. So in our subsample chroma, we use one 4x4 transform, which then covers the same spatial extent as multiple Luma blocks. So how do you decide what mode information to use? And the answer is we look at the bottom right Luma block from whatever that subdivision was, and that determines if you have an intra block or an inter block. So as a result, that means that you can actually have some of the blocks in this sub 8x8 region are intercoded, but the chroma winds up being intra-coded. So now we have to buffer Luma from the intercoded pixels as well as the intracoded pixels in the sub 8x8 regions, and that might be a surprise. And in fact, we've implemented this incorrectly at the moment, but we'll fix that. And then the next complication is doing chroma DC prediction for non-square blocks. So what happens is that the DC prediction works by basically summing up all the pixels to the left and summing up all the pixels above and then taking an average. And when your blocks aren't square, the number of pixels in that sum is not a power of 2. So now you have to actually do a division. But the number of different cases there is pretty small, so we can just implement that division with the lookup table because dividing by either 2 or 3 is not that hard. And AV1 turns out to be adding rectangular transforms with rectangular interprediction, so they're going to have to solve this problem anyway. And so we'll probably wind up using the same mechanism they did when it comes time for that. Next slide. And then finally, there's all sorts of fun at the boundaries of the frames. So what happens in AV1 is that your frame size gets rounded up to the nearest multiple of 8, but block sizes in AV1 can actually be much larger than 8 by 8. They can be up to 64 by 64.
28.
So yeah, maybe 128 by 128 someday. And so if you have a large prediction block which overlaps this boundary, but smaller transform blocks inside that large prediction block, some of your transform blocks may be entirely outside that boundary, and those just don't get coded. Which, okay, that's fine, until you also realize that your chroma transform blocks can actually cover a larger area than the corresponding luma transform blocks. And this might be easier to see if you go to the next slide where there's a picture. So here's an example of when this happens. If I have a 32 by 32 prediction block with 8 by 8 transforms inside of it, in the luma plane, it looks like this. You know, as it runs into this frame boundary, you know, the last 4 blocks there are just not coded. Like they just don't appear in the bit stream. But for a 32 by 32 prediction block with 8 by 8 transforms in the luma plane, the corresponding transform size in the chroma plane for 420 is also 8 by 8, which means it actually covers 4 times the area of a corresponding luma transform block. So now those blocks partially overlap that boundary, and since they're not completely outside, they still get coded, which now means I have a bunch of chroma pixels where there is no corresponding luma pixel to draw a prediction from. And so currently what we're doing is just taking the last row of luma pixels and extending them downwards, which, you know, is simple and seems to work okay-ish. This, by the way, boundary handling also complicates DC prediction quite a bit when your neighbor's block sizes don't match up with your own block sizes, but that complication is, again, not CFL specific. I just thought I would point it out.
It's literally just 1 pixel extrapolation?
It is literally 1 pixel extrapolation. We could have tried to do something more expensive, but it didn't seem worth it.
Does it actually matter?
It has a small effect on metrics. I doubt anyone would notice looking at the images. And ultimately, I have a completely different set of proposals that I hope will clear all of this up, but I have no idea if they'll work yet, for simplifying how all of this is handled. And not just for CFL, but for the whole codec. So I don't want to invest a huge amount of time in over-engineering how CFL handles
It
this.
just seems like ultimately your decoder isn't going to emit those things outside the frame boundary anyway, isn't it? So what does it matter what you predict the chroma to be?
Yes, exactly. And the answer is you still have to make an encoder smart enough to encode something for them that doesn't affect other things, right? Because transform coefficients ring across the whole block. So I've included these nice outdated example images. These are about a month old, so they're not that outdated, but things have changed since they were generated. So this is current AV1, and the next slide is when we add CFL, and I don't know if you can see that basically we just get a huge amount of additional detail. So I think this is just the chroma red plane, and it's over 1 dB of improved PSNR. So this is a picture of the Valle de Coca, which is basically a bunch of cliffs and a lake. It wasn't foggy, in fact.
This is just 1 chroma plane, right?
Yeah, this is just the CR plane.
And in grayscale, not the actual chroma color that you're,
Right,
that you're coding.
yes. Right. And looking at the objective results, so these are measured just on still images since this is an intra-prediction mode, so it does not have a large impact on interframes. We're basically trading off about 0.3% BD rate for PSNR to gain 5% for CIED 2000. And so CIED 2000 is a metric which actually contains both Luma and Chroma approximately weighted perceptually. So it's doing CIE lab conversion and then computing delta E. So it behaves very similar to PSNR, but has a perceptual weight for Chroma in it. And so, you usually sort of expect that sort of small changes in Luma can generate large changes in Chroma, but one CIED takes Luma into account, and 2.3 for 5 seems like a pretty reasonable trade-off. But we'd like to shift some of those gains back into Luma, so we're also working on adjusting the Luma Chroma balance in the encoder, but currently none of that is at all sane in the way the encoder works. It actually has different parts of the encoder using completely different weights. And so we're trying to sort that mess out, and then maybe we'll have a parameter we can tune to move some of those gains from Chroma back into Luma and have green numbers across the board. But all right, I think that's it. Are there any questions?
Snell, it's Morgan from Cisco. Does it make sense to use implicitly derived alpha values as prediction for the signal alpha values in order to reduce the bit cost?
So we tried that in Dala and basically didn't help. That may be worth revisiting for AV1, but it has a decoder complexity cost, and so the question is the savings worth the extra CPU required to do the implicit model building? And the answer is, maybe. We haven't tried it.
So the question was the encoder and decoder both search for alphas, and then you only predict them, and then only the error of the prediction is signaled?
Yeah, so I think that's what Steiner was suggesting.
You did try it?
So we tried it in Dala. We have not tried it in AV1 with this new proposal. All right. Any other questions? All right. Thank you.
So a little over our agenda, but there is time left in this session if anyone wants to raise anything else. Otherwise, you can take off early.
Cool. Did everyone sign the blue sheets? Anybody didn't sign the blue sheets? Okay, cool, Magnus. I'll get the blue sheets to you. And Tessa, if you don't mind sending the notes to video-codec, I'll go and come speak to you. And yeah, thank you, Jonathan, for doing Scribe the Jabber. You're free. Yes. Go about your merry way.
And please make sure to get the blue sheets signed if you came in afterwards.
Downstairs, I basically did not have a connection at all. Yeah, I was like,
I'll take the sheets to the people.